Hi everyone, welcome back to my geometry videos. In this tutorial I'd like to talk about similarity. We need to develop some techniques to prove triangles are similar. The most fundamental is the angle postulate, which says if all three angles of one triangle are congruent to their corresponding angles of a second triangle, then the triangles are similar. So we accept the angle postulate without proof. We can use the angle method for proving similarity between triangles. So we're given triangle ABC and triangle DEF. We're given that angle A is congruent to angle D and angle B is congruent to angle E. And we want to prove that triangle ABC is similar to triangle DEF. So we write down the givens, and we can apply the no choice theorem to triangle ABC and triangle DEF. And that leaves angle C is congruent to angle F. Therefore, by the angle postulate and using these three facts, we know that triangle ABC is similar to triangle DEF. We're going to be using the AA method the most for proving similarity between triangles. So there are two other less commonly used methods to prove triangle similarity. There's the side tilde method, so don't confuse this with the side method for congruence. This method here says if all sides of one triangle are proportional to the corresponding sides of a second triangle, then these two triangles are going to be similar. So we need to know all the sides are in proportion in order to apply this theorem. The other one's SAS tilde, so side angle side for similar triangles. Don't confuse this with the side angle side method for congruences. So, and using this method, we have to know that two sides of one triangle are proportional to their corresponding sides in the second triangle, and we have to know that the angle between these two sides we pick is going to be congruent. So in other words, if length of AB divided by length of DE equals length of AC divided by length of DF, and we know that angle A is congruent to angle D, then triangle ABC is proportional to triangle DF. Using this method, we don't have to know beforehand that length of BC divided by length of EF is equal to this proportion over here. So let's do some problems to make this clear. So we're given that ABCD is a trapezoid with bases AB and CD, and we want to prove that triangle EAB is similar to triangle EDC. So we write down what we know. And we know a trapezoid has exactly one pair of parallel sides, so the bases, right? So segment AB is parallel to segment CD. Given this setup, we should think about alternate interior angles, right? If a transversal intersects two parallel coplanar lines, alternate interior angles are congruent. So we can use this segment AD as a transversal, right? So we have this angle here, BAE, right? And then we have this angle here, CDE, right? They're both in the interior region, bounded by segments AB and CD, and they're on opposite sides of the transversal, right? So actually, to be more thorough, you could say that angle BAD is congruent to angle CDA because we're taking AD as the entire transversal, but I'm using this because we're going to be working with these two triangles. So okay, so angle AEB is congruent to angle DEC. Why? Because these are vertical angles, right? It looks like these two V shapes, they're upside down and they meet at this common point. So, and we know vertical angles are congruent, so angle AEB is congruent to angle DEC. And by the angle-angle postulate, we know that triangle EAB is similar to triangle EDB. Notice how how I order the letters is important, right? We did this. We proved that this angle was congruent to this angle, right? So A matches up with D, right? So let's move on to another problem. So here we're given this triangle, a larger triangle ADE, and then we have these two smaller triangles that are kind of like inside, right? So we're given that segment DC is perpendicular to segment AE, and segment EB is perpendicular to segment AD. And we want to prove that triangle ACD is similar to triangle ABE. So write down our givens, and we know that perpendicular segments meet at right angles, right? So, this angle DCA, this angle here, is going to be a right angle, right? And angle EBA is also going to be a right angle, right? Because of these two segments being perpendicular. And we also know that all right angles are congruent. So in other words, angle DCA is congruent to angle EBA. Now I can apply the reflexive property of congruence. Angle A is congruent to angle A. And then we have all we need. We have the two angles, right, for the triangle. So we have, this angle A, which is going to be the same for both of these triangles. And we know that by 4 that the other angles are going to be congruent, right? The other two angles we need. So we know that triangle ACD is similar to triangle ABE, which is what we wanted to prove. Okay, so here's an example. I'll try to use the side angle side similarity postulate or theorem to prove that these two triangles are similar. You don't usually use this a lot, but I'll give an example where you can use it. So we're given that triangle ABC and triangle DF are isosceles, and that angle A is congruent to angle D. Prove that triangle ABC is similar to triangle DEF. So we write down our givens, right? And we know since these two triangles are both isosceles, right, they have at least two congruent sides. So we're going to say segment AB is congruent to segment AC, and segment DE is congruent to segment DF. I'm going to apply the definition of segment congruent. So I'm just going to shorthand here. So AB means the length of segment AB. So makes it a little bit easier than just writing this out completely. So I'll just say that from 4, AB is equal to AC, and from 5, DE is equal to DF. Now, we know that lengths are not equal to 0, right, in a triangle when we're dealing with these different segments. So we can divide. So using the property of division and using the fact that DE is not equal to 0 and DF is not equal to 0, then AB divided by DE is equal to AC divided by DF. So in other words, we found the proportion we wanted, right? AB divided by its corresponding side DE is equal to AC divided by its corresponding side DF. And we also know that the angle between those two in this proportion is congruent, right? These two angles are congruent. So we know that triangle ABC is similar to triangle DEF by the side angle side similarity theorem. So this last problem is challenging. We're given that triangle ABC is similar to triangle DEF, and triangle ABC is similar to triangle GHI. And we want to prove that triangle GHI is similar to triangle DEF. So I write down what we're given, and using statement 1, we know that AB divided by DE, so we match the first two letters of the first triangle with the first two letters of the second triangle, is equal to AC divided by DF, which is equal to BC divided by EF. So this last two matches with the last two. So I didn't draw the triangles, but this is why it's so important to make sure that you get the ordering right when you're dealing with triangles in either congruences or in similarities, right? Because they tell you all the information about corresponding sides and all that. So, and we also know that angle A is going to be congruent to angle D, angle B is going to be congruent to angle E, and angle C is going to be congruent to angle F, because in similar triangles, corresponding angles are congruent. I'm going to do the same thing to our second triangle here, our second relation here. So we're given that AB, so actually I did it the opposite way. So GH divided by AB is going to be equal to GI divided by AC, which is equal to HI divided by BC. So you're just using the same thing. It doesn't matter which way you take the proportion, because it's going to remain the same, right? So just use the same justification. In similar triangles, lengths of corresponding sides are proportional. And we can also use the fact that in similar triangles, corresponding angles are congruent. So you get A is congruent to G, B is congruent to H, and C is congruent to I. So I'm going to use a little trick using the property of equalities. I can multiply the equality in 3 by GH divided by AB, and I'm going to distribute it. So you get GH divided by AB times AB divided by DE is equal to GH over AB times AC divided by DF, and then the last term, right? That's just algebra. And then I'm going to use what I have in 5. We're given that GH over AB is equal to GI over AC. So I'm going to substitute the second GH divided by AB with GI over AC. And then in the same way, I know that GH over AB is equal to HI divided by BC. So I'm going to substitute GH divided by AB with HI divided by BC in the last element, right, over here. So if you do the algebra and you simplify, you get GH divided by DE is equal to GI divided by DF, which is equal to HI divided by EF. And we also know that angles that are congruent to the same angles are congruent. So we know that angle A is congruent to both angle D and angle G. So angle D and angle G are congruent. Angle E and angle H are congruent to the same angle B. So angle H is congruent to angle E, and angle C, angle F and angle I are congruent to the same angle C. So angle I and angle F are congruent. So using 9 and 10 and using the definition of similarity, we see that triangle GHI is similar to triangle DF, which is what we want to prove. And we could double check, right? Let's see to match up the corresponding sides. GH matches up with DE, right? GI should match up with DF. HI should match up with EF. And then G should match up with D, H should match up with E, and I should match up with F. So that finishes my tutorial, my second tutorial on similarity. There's going to be 1 or 2 more videos on similarity, but I hope you enjoyed this video and I hope you found it helpful, and I hope to see you during my next tutorial. Alright, take care everyone. Bye.